mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Hi, and welcome back to Distance Learning or Online Learning with Mr. Weeb. I hope things are going well for you. We're into day 4 of this mode of delivery, and I hope that you're able to watch the videos, and I hope that you're able to get on to Connect. I know there's been some issues getting on to Connect, but I know that Connect, the host site, is working on fixing some of those issues, and I hope that it works well and you're able to get on. Yesterday we were talking about electric forces and net electric forces, and I gave you a few questions, and I realized after the fact that I had assigned the same textbook questions 2 days in a row, but at least you had the handout. There were 3 questions on the handout on net electric forces that you could do. I did have a question about question number 1. Question number 1 had charged particles in the corners of an equilateral triangle, so it had you doing some trigonometry work again. I do want to go over that question before we get into anything else today, which actually today is going to be a really, really light lesson. In fact, no new content today, but we'll go over this question and we'll go from there. So on the board behind me we have question 1, and I've kind of set it up and I'll kind of walk you through it. You'll be able to have a permanent record of this question from the video. And so we'll walk through it, and hopefully you get it. If you have any questions, again, make sure you email me. You can even put it into Connect if you want to, but email's been working fine. I've received several emails from people, and it has worked well, so I want to continue to do that if possible. All right, so here we go. We have the 3 charged particles. They're 3 negatively charged particles. They're placed at the corners of an equilateral triangle with side lengths of 20 centimeters. The charge on each particle is 4 times 10 to the negative 6 coulombs. So that's the question. And then the question says, find the net force on each sphere. Now, first thing you have to realize is that the net force on each sphere is going to be the same. All 3 charged particles are the same. All 3 distances between them are the same. And so the net force on all 3 is going to be the same number, which means we don't have to find the net force on all 3. We have to find the net force on one of them, and then it will be the same for the other 2. So I chose sphere C. I'm going to find the net force on C, and then that will be what we'll do. So first thing we're going to realize is we're going to find our forces. So they're all negatively charged, so there's a bunch of forces of repulsion here. So C is going to be repelled by B in this direction, so we pushed to the right with a force. We'll call that force 1. It's going to be repelled from A in the direction downward here and to the right. We'll call that F2. And now intuitively, you know that if this was the case, your net force would be somewhere in between here, right? You know that. You know that, right? There's no way about it. So we're going to find those forces first. They're going to be the same number again because same charges, same distance. So F1 will equal to F2. Our formula, K, Q1, Q2 over R squared. Our constant, K, 9 times 10 to the 9 newtons meters squared per coulomb squared. The charge is 4.0 times 10 to the negative 6 coulombs squared over the distance between them, which is 0.2 meters. And then we're going to square that as well. And so punch that into our calculator, and we should be able to get 3.6 newtons. So coming back to our diagram here now, we know that these numbers are 3.6 newtons. Okay, so that's step 1. Step 2 now is to recognize that this isn't in a straight line. These are angles, and so we have to do some vector addition. We're still going to do F net equals F1 plus F2, but because it's not in a straight line, we have to add the vectors together. So we're going to take our vector that's to the right. We're going to place it tip to tail with our vector that's on the angle, and label them 3.6 and 3.6. And that means our answer, our net force, is the sum of these two, and the sum is, again, the vector that goes from the beginning to the end. So that's our F net. Now, we have a triangle. It's not a right triangle. We have two side lengths. Currently, we don't have any angles that are labeled, but we do know some angles. If we go back to our original diagram, this is an equilateral triangle. Well, we know that in an equilateral triangle, all the angles are 60 degrees. So we can label that. That also then makes the angle between these two 60 degrees. And when I take this line and move it over here, right, this is essentially what I've done. I've taken this vector and placed it tip to tail with this one here. That's going to make the angle inside this triangle 120 degrees. And we can see that it's an equilateral triangle there as well, which is going to make this angle 30 degrees. And this one as well, but we don't need this angle for anything, so I'm not going to label it. All right, so now what I've got is I've got a triangle. I've got two sides. I've got the angle between them. It's not a right triangle. With this information, we're going to go back to our knowledge of pre-calculus and realize that to solve this triangle, we need the cosine law. So, remember cosine law? Cosine law, you've got it on a formula sheet. It is c squared equals a squared plus b squared minus 2ab cos c. Here it is written out now, so f net is what we're solving for. So f net squared is going to equal the one side, 3.6 squared, plus the other side, 3.6 squared, minus 2 times the two sides, so times 3.6 and 3.6, times the cosine of the angle that's between the two sides, so cosine of 120. We're going to punch this into our calculator. We're going to take the square root, and we'll get an F net of 6.2 newtons. Okay? Now, we're not quite done. It is a vector, so we do need a direction. And again, this angle in here is 30 degrees. And so we could simply write that this is, as a direction, we could say that it is right 30 degrees down. That would be totally fine. It expresses this diagram the way I have it drawn here as to the right and 30 degrees down. I know in the textbook it said that the angle was 150 degrees from each side of the triangle, and so that would be if we were to draw our line in here, go right here along here, and this angle would be our 150 degrees. You don't need to do that. However you express the direction is up to you, as long as it expresses the direction properly. If I read the answer here and I can match it to your diagram and it expresses the right direction, then you will have it right. All right. If you have any questions on that, please contact me, send me an email, and I can go over whatever we need to go over there. So here's question 2 from yesterday's assignment. I'm going to walk you through what I've done here, and hopefully it'll make sense for you. So as we look at this question, we have our 3 charged particles, A, B, and C. They're equally spaced 0.5 meters apart. The first 2 are a negative, and the third one being a positive charge. And of course, you on the paper have their charges, but just to remind you, this one is 4 times 10 to the negative 6 coulombs. This one is 6 times 10 to the negative 6 coulombs. And this third particle is 9 times 10 to the negative 6 coulombs. We've got our formula over here. We're going to use this formula extensively, so I've written it here, and I'm not going to write it as we do the rest of the question. You can. All right, so what we need to do, we need to recognize that there are 3 different forces at play here. There's a force between A and B, there's a force between A and C, and there's a force between B and C. So the first thing we're going to do is we're going to find all 3 of those forces, and so that's my calculations here are. Here I've got FAB, the force between A and B. I've got my filled in numbers here, and that will equal 0.86 newtons. And you'll notice I have not put a direction on here yet. We'll get to that in a minute. Okay, then we found FAC. Again, put our numbers in. The only number that changes is this last one for the third charged particle, and the distance is now 1 meter instead of 0.5, and we get 0.32 newtons. Again, no units or no direction yet. And then we'll find FBC. Okay, and FBC is again the force between B and C. Distance is again 0.5. Got our appropriate charges, and that will give us an answer of 1.9 newtons. Now, once we have these, now what we have to do is we have to realize what we're doing here. So if I'm going to look at sphere A, charged particle A here, charged particle A is going to be repelled by B. So FAB is going to be acting toward the left, while FAC, between A and C, that's a force of attraction, so A would feel a force to the right. So we have FAB acting to the left, FAC acting to the right. When I find the net force again being the sum of the forces acting on A, we are going to take FAB and we're going to subtract FAC. So 0.86 minus 0.32 gives us 0.54, and that will be to the left. And so that's, of course, the answer on the sheet is 0.54 to the left. We're going to repeat that process for sphere B and C. For B, it's going to experience a repulsion force from A, so FAB is going to be to the right, but it's going to experience an attraction force from C, so FBC is also to the right, and so I'm going to take both those numbers, my FAB, which is 0.86, and my FBC, which is 1.9, and I'm going to add those together. They're both in the same direction, so our F net is going to be the sum of those two forces, and they're in the same direction, so we'll add them. So 1.9 plus 0.86 gives us that 2.8 number to the right. That is the answer on the sheet. And you repeat the process for the third sphere. We have FAC being an attractive force to the left. FBC is also an attractive force to the left. So we are going to add those two numbers together. So that's our 0.32 plus 0.19, giving us our 0.22, 0.23 answer that is on the page. And that's how you do that question. Find the forces, isolate each sphere, realize what the forces are that are acting on that sphere, and add the appropriate numbers. I hope that makes sense. Again, if it doesn't make sense, shoot me an email, and we'll try to clarify things further. I'm going to do question 3 on the other board right away. Here we go. Okay, here we are with question 3 off yesterday's assignment. So in question 3, here we got to do a little bit of math, and I didn't finish the problem for you. I'm going to get you to do a little bit of work to finish it to see if you can still do this stuff, because it's a little bit of algebra that you have to do at the end. All right, so here's our situation. We've got A and B, our two particles that are situated 2 meters apart. In the middle, I've placed object C, or charged sphere C, and I've made it the opposite charge negative. And it doesn't matter if you made the two outside ones negative and the middle one positive. It really doesn't matter one way or the other. All right, and I've labeled now, because we want to find the distance, where should it be placed? I've labeled the distance between A and C as x, and I've labeled the distance between C and B as 2 minus x, right? The whole distance is 2 meters, and this is x. This distance is 2 minus x. Again, here's my formula, F equals K, Q1, Q2 over R squared, that we're going to use throughout this problem. Now, in order for C to experience no net force, I want the net force to be 0, that means that the two forces, FAC and FBC, have to be equal. Right, that makes sense, they have to be equal, and they're going to act in opposite directions, which means we're going to have a 0 net force. So, filled in my formulas here on both sides, and what I want you to realize here is that because there's a K on both sides of the equation, I can divide both sides by K, and it cancels out. And this Q2, this is the charge on sphere C, right? We'd have A and C, and we'd have B and C. So Q2 on both sides of the equation is the same number as well, so we can divide both sides by it, and it will cancel out. All right, so that leaves us with the charge on sphere A, 1.6 times 10 to the negative 5 coulombs over x squared, the distance between A and C. And on the other side, we have our charge on sphere B, which is 6.4 times 10 to the negative 5, and the distance between C and B, 2 minus x squared. Okay, at this point, I'm going to divide both sides by 10 to the negative 5, because they'll cancel out, and I'm going to cross multiply. So that leaves us with this statement right here. Okay, this one here, 1.6 times 2 minus x squared equals 6.4 x squared. Now, to make the math easier, this is a little bit tricky to see, and you don't have to do this, but it makes it easier. If you divide both sides by 1.6, it gets rid of it here, and 1.6 goes evenly into 6.4 4 times. So we get a nice easy statement here. 2 minus x squared equals 4x squared. On the left-hand side, we're going to multiply it out, giving us 4 minus 4x plus x squared equals 4x squared. We're going to bring everything onto one side and move everything onto the right side, but then switch it around. And we're going to get left with 3x squared plus 4x minus 4. All right, now this is where I'm going to leave it, and you're going to work towards getting the answers. The answers are written on the board right over here. Okay, you're going to get 2 answers when you solve this because you are going to recognize this as a quadratic equation. And to solve a quadratic equation, you have 2 options, right? You're going to either use the quadratic formula or you're going to try to factor it. I'll tell you that this doesn't factor, so you're going to use the quadratic formula. So hopefully you remember that. If you don't, you can look it up in your pre-calculus work from first semester and do that. So you're going to plug these numbers, A, B, and C, into the quadratic formula. And we are going to get our answers that are in the blue box in the corner there. Mr. Peters is making a surprise appearance. Say hi to Mr. Peters. See ya.
Bye.
And that's the end of the question. Hopefully that makes sense. Again, shoot me an email if you need more explanation on that. And that brings us to the end of today's lesson. I'm not going to give you anything new today. On Connect, you'll find your assignment. It'll be out of your textbook. It's a bit of a review at the end of chapter 20 in your textbook. So we're going to work on that. And hopefully that will make sense. Tomorrow we're going to do something a little different. For Friday's class, I'm going to hold a little bit of a virtual class. What I want you to do today sometime is set up a Zoom account. Just Google Zoom and find the Zoom app and get an account going there. And Zoom is just a video conferencing piece of software. And I want you to sign up for an account, which is free. Use your email. And we're going to get you, I'll send you an email and put some instructions on Connect as to how we will connect together as a class, and hopefully we'll be able to do a little quick check-in. And we're going to do that at 11 o'clock on Friday, so try to plan for that tomorrow. And hopefully we'll see you all, as it's a little bit of a video conferencing thing. In terms of our verse of the day today, our verse of the day comes from Psalm 94. Just open it up here. So it's Psalm 94, verses 18 and 19. Again, this is a timely verse. I thought it was quite timely for today. Here it is. It's David talking to God. He says, and David says, "When I said, my foot is slipping, your unfailing love, Lord, supported me. When anxiety was great within me, your consolation brought me joy." So I thought that was fairly timely in terms of what's going on in the world these days. Just remember that the Lord's got it. He's got you. He's supporting you. He was in control months ago, he's in control today, and he'll be in control again, or he is still in control today and will be tomorrow as well. And so we can trust in that, and that can bring us comfort, and that can bring us joy. Have a great day, and hopefully we will be able to see you on our video chat on Friday. See ya.